Hello student, today we shall discuss 8085 microprocessor. Yes, the 8085 microprocessor architecture and its buses. The 8085 is an 8-bit general purpose microprocessor that can address 64 kilobyte of memory. It has 40 pins and uses plus 5 volts for power. It can run at a maximum frequency of 3 MHz. The pins on the chip can be grouped into 6 groups: address bus, data bus, control and status signal, power supply and frequency, externally initiated signal, serial I/O ports. Address bus means a set of wires which carries address of the memory location. Because 8085 addresses 64 kilobyte of memory, so the width of the address bus must be 16-bit. As we know that it is an 8-bit microprocessor, so data bus, the width of the data bus must be 8-bit. In addition of these two, means address bus carries address of the memory location, data bus carries data to be operated. In addition of these two signals, we require control and status signals. There are various control and status signals are available: I/O, M bar, like this. Also we require power supply and every clock signal to operate 8085. Then externally initiated signals means for interrupts, and we have serial I/O ports. Means microprocessor is a 8-bit, but if we communicate one processor to other processor, we communicate serially. So we require the serial I/O ports. The address and data bus. The address bus has an 8 signal lines, A8 to A15, which are unidirectional, only one direction. The other 8 address bits are multiplexed, that is time shared, with the 8 data bits. So the bits AD0 to AD7 are bidirectional and serve as A0 to A7 and A0 D0 to D7 at the same time. So initially AD0 to AD7 carries address. After address, these address lines becomes free. So then the same bus AD0 to AD7, same bus acts as a data bus. So they are multiplexed together, time division multiplexing, okay, at different times. Okay, initially the bus carries address. After some time, the same bus carries data. This is called time division multiplexed. During the execution of the instruction, These lines carry the address bits during the early part, then during the later part of the execution, they carry the 8 data bits. In order to separate the address from the data, we can use a latch to save the value before the function of the bit changes. Then the control and status signals. There are 4 main control and status signals are available. These are ALE, address latch enable. The signal is a pulse that becomes 1 when the AD0 to AD7 lines have an address on them. It becomes 0 after that. This signal can be used to enable a latch to save the address bits from the address and data lines. Read. Read is a control signal. It is active low. Write is also a control signal. It is active low. Read means whenever we require to read from the memory, this signal becomes 0. Whenever we want to write something into the memory, this write signal becomes 0. Then IOM bar. This signal specifies whether the operation is a memory operation or an IO input output operation. If IOM bar is equal to 0, it means memory related operation is working. If IOM bar signal is 1, it means input output device or operation is working. S1 and S0 are called status signals to specify the kind of operation being performed, usually unused in a small systems. Frequency and control signals. There are 3 important pins in the frequency control group. X0, X1 are the inputs from the crystal or clock generating circuit. The frequency is internally divided by 2. So, to run the microprocessor at 3 MHz, a clock running at 6 MHz should be connected to the X0 and X1 pins. Clock out. An output clock pin to drive the clock of the rest of the system. We will discuss the rest of the control signal as we get to them. Microprocessor communication and bus timing. To understand how the microprocessor operates and uses these different signals, we should study the process of communication between the microprocessor and memory during a memory read or write operation. Let us look at timing and the data flow of an instruction fetch operation. Step for fetching an instruction. Let us assume that we are trying to fetch the instruction at memory location 2005. That means that the program counter is now set to that value. The following is the sequence of operations. The program counter places the address value on the address bus. and the control issues a read bar signal. The memory's address decoder gets the value and determines which memory location is being accessed. The value in the memory location is placed on the data bus. The value on the data bus is read into the instruction decoder inside the microprocessor. After decoding the instruction, the control unit issues the proper control signals to perform the operation. Now, let us look at the exact timing of this sequence of event, as that is extremely important. At T1, the higher order 8 address bits, that is 20H, are placed on the address lines, that is dedicated address lines A8 to A15, and the lower order address bits are placed on the multiplexed address and data bus AD7 to AD0. The address latch enable, that is ALE signal, goes high to indicate that AD0 to AD7 are carrying an address. At exactly the same time, the IO-MBAR signal goes low to indicate a memory operation, means we require to read something from the memory. So it indicates IO-MBAR 0 indicates the operation is memory related operation. At the beginning of the T2 cycle, the lower order 8-bit address are removed from AD0 to AD7, and the controller sends the read, that is RD bar signal, to the memory. The signal remains low for 2 clock periods to allow for slow devices. During T2, memory places the data from the memory location on the line AD0 to AD7. During T3, the read bar signal is disabled, goes high. This turns off the output tri-state buffer in the memory. That makes the AD0 to AD7 lines go to high impedance mode. From the above description, it becomes obvious that the AD0 to AD7 lines are serving a dual purpose, and that they need to be demultiplexed to get all the information. The high order bits of the address remains on the bus for 3 clock periods. However, the low order bits remains for only 1 clock period, and they would be lost if they are not saved externally. Also, notice that the lower order bits of the address disappear when they are needed most. To make sure we have the entire address for the full 3 clock cycles, we will use an external latch to save the value of AD7 to AD0 when it is carrying the address bits. We use the ALE signal to enable this latch. Now, this circuit gives the demultiplexing of AD0 to AD7. Higher order address bits A8 to A15 is directly or dedicated bus. They need not require any demultiplexing. But lower order data and address bus AD0 to AD7 initially at T1 state it carries address. This address must be latched or stored somewhere. So using a digital latch we store these AD0 to AD7. Then this bus is made free for data communication. Given that ALE operates as a pulse during T1, we will be able to latch the address. Then, when ALE goes low, the address is saved and the AD0 to AD7 lines can be used for their purpose as the bidirectional data lines. Cycles and status. From the above discussion, we can define terms that will become handy later on. T-state, one subdivision of an operation. A T-states last for one clock period. An instruction execution length is usually measured in a number of T-states or clock cycles. Machine cycle, the time required to complete one operation of accessing memory. RIO, or acknowledging an external request. This cycle may consist of 3 to 6 T-states. Instruction cycle, the time required to complete the execution of an instruction. In the 8085, an instruction cycle may consist of 1 to 6 machine cycles. Generating control signals. The 8085 generates a signal, RD bar signal, that is called read bar signal. However, signal need to be used with both memory and IO read. So, it must be combined with the IOM bar signal to generate different control signals for the memory and IO. Keeping in mind the operation of the IOM bar signal, we can use the following circuitry to generate the right set of signals. So this circuit has 3 inputs: IOM bar, read bar and write bar, and it gives 4 outputs, control signals. These 4 are the control signals. It has 3 inputs and 4 output. It accepts 3 input and it generates 4 output: memory read bar, memory write bar, IO read bar and IO write bar. Okay, yes. A closer look at the 8085 architecture. Previously we discussed the 8085 from a programmer perspective. Now let us look at some its features with more detail. The ALU. ALU means arithmetic and logic unit. In addition to the arithmetic and logic circuit, The ALU includes the accumulator, which is part of every arithmetic and logic operation. Also, the ALU includes a temporary register. It is an 8-bit register used for holding data temporarily during the execution of the operation. This temporary register is not accessible by the programmer, means we cannot able to store or we cannot able to modify the content of this temporary register with the help of instructions or with the help of program. So this is not accessible to the programmer. The flag register. There is also the flag register whose bits are affected by the arithmetic and logic operations. Yes, that is sign flag. The sign flag is set if bit D7 of the accumulator is set after an arithmetic or logical operation. Okay. In other words, whatever the D7 of accumulator, it is the sign flag. Okay, so Z0 flag, this 0 flag set if the result of the ALU operation is 0, otherwise it is reset. This flag is affected by operations on the accumulator as well as other registers. Auxiliary carry. This flag is set when a carry is generated from bit D3 and passed to D4. This flag is used only internally for BCD operations. BCD means binary coded decimal operations. Parity flag. After an ALU operation, if the result has an even number of ones, the parity flag is set. Otherwise, it is cleared. So, the flag can be used to indicate even parity. Carry flag. Carry flag is set whenever a carry appears when an arithmetic and logical operation is performed by the ALU. The 8085 executes several types of instructions, with each requiring a different number of operations of different types. However, the operations can be grouped into small set. The three main types are memory read and memory write, IO read and IO write, then last request acknowledge. These can be further divided into various operations or machine cycles. Opcode fetch machine cycle. The first step of executing any instruction is the opcode fetch cycle. In this cycle, the microprocessor brings in the instructions opcode from memory. To differentiate this machine cycle from the very similar memory read cycle, The control and status signals are set as follows. IOM bar signal is set to 0 because it is memory read operation, memory related operation. Then S0 and S1 are both 1. It means fetch operation is going on. This machine cycle has 4 T states. The 8085 uses the first 3 states to fetch the operation code or opcode. T4 is used to decode and execute the opcode. It is also possible for an instruction to have 6 T states in an opcode fetch machine cycle. The memory read machine cycle is exactly the same as the opcode fetch, except it only has 3 states. The S0 signal is set to 0 instead. S1 is set to 1. The memory read machine cycle. To understand memory read machine cycle, let us study the execution of the following instruction. Assume that program is stored in 2000 and 2001, 3E and 32. That is, move immediate A32. This instruction says that a constant number 32 is stored in the accumulator. In memory, these instructions looks like the first byte 3E represents where 3H means 3E is an hexadecimal number. The first byte 3H represents the opcode for loading a byte into the accumulator. The second byte is the data to be loaded into the accumulator. The 8051 needs to read these 2 bytes from memory before it can execute the instruction. Therefore, it will need at least 2 machine cycles. The first machine cycle is the opcode fetch discussed earlier. The second machine cycle is the memory read cycle. Machine cycles and instructions length do not have a direct relationship. To illustrate, let us look at the machine cycle needed to execute the following instruction. STA 2065H store accumulator direct. It means the content of accumulator, a number which is stored in the accumulator, is moved or copied into the memory location 2065. This is a 3-byte instruction requiring 4 machine cycles and 13 T states. The machine code will be stored in memory as shown in the right. In 2010, 32 is stored. In 2011, 65H is stored. 2012, 20 is stored. This instruction requires the following 4 machine cycles. the opcode fetch. To fetch the opcode 32H from location 2010, decode it and determines that two more bytes are needed. Memory read to read the lower order bytes of the address, that is 65H. Memory read to read the higher order byte of the address 20H. A memory write to write the contents of the accumulator into the memory location. In memory write operation, the 8085 places the address 2065 on the address bus, identifies the operation as a memory write, that is IO M bar is equal to 0, S1 is equal to 0, S0 is equal to 1, places the content of the accumulator on the data bus and asserts the signal write bar. During the last state, the content of the data bus are saved into the memory location. Memory interfacing. There needs to be a lot of interaction between the microprocessor and the memory for the exchange of information during program execution. Memory has its requirements on a control signal and their timing. The microprocessor has its requirement as well. The interfacing operation is simply the matching of these requirements. Memory structure and its requirement. The process of interfacing the above two chips is the same. However, the ROM does not have write signal. We have two types of memory. One is RAM, read-write memory. It requires a read signal to read the data from this memory, and we require write signal to write something into this memory. And we have chip select signal. When this chip select signal goes low, then only this memory is active or selected. ROM, read only memory. In this memory, we cannot write anything. We can only read, or we can only retrieve the data which is previously stored on this memory. So it does not require any write signal. Okay, we cannot able to write anything on it. We can only read data already stored in it. Yes. Accessing memory can be summarized into the following three steps. Select the chip, identify the memory register, enable the appropriate buffer. Translating this to microprocessor domain. The microprocessor places a 16-bit address on the address bus. Part of the address bus will select the chip and the other part will go through the address decoder to select the register. The signal IOM bar and read bar combined indicate that a memory read operation is in progress. The memory read signal can be used to enable the read line on the memory chip. So this is all about this class. We can continue in the